Buongiorno, sehr verehrte Damen und Herren, liebe Ehrengäste, dear colleagues and friends. I'm switching back to English now, that's all I'm saying in German and Italian. It's a great pleasure to be here, and as Thomas already indicated, I've been connected in many different ways to CSCS for more than a decade, and I very briefly want to talk about some of the connections and show you two images and two pictures just to connect back to this beautiful building that you have here. There are many, as I said, many interactions between CSCS, but the new facility that you're in has some connections to this hole in the ground that we're currently still digging in Berkeley. And the story here is that in about 2004, 2005, we started there a new computer building. And then I talked with colleagues here, and they said, can we come and exchange notes? And there were a number of exchanges, visitors coming from Lugano or from Mano to Berkeley and back. And lo and behold, here we are in fall or summer of 2012, and CSCS is dedicating this wonderful building, and we're still digging the ground. And I want to make one very, very important point, because all the local dignitaries are here. The reason why this is happening is because you have a wonderful collaboration with the city, with the canton, with the university administration, and with the federal administration. So you need all players to work together. We did not have this. We had 3 lawsuits. And I think maybe I can make the usual comment about American lawyers. There are just too many around. We have also too many citizens who don't like anything, and the first thing they do is go to a lawyer. So congratulations, not just on completing this building, but congratulations on having built a community around the building and the center that is truly supportive of what you're doing here. So, of course, these are our visions in Berkeley, and I hope that maybe some of you will find their way to California, and we can welcome you to the dedication in 2 years. So here you are, and I would like to connect to 2 previous talks that were actually very great introductions. In particular, Domenico Scardini's talk was answering the first question. I want to talk a little bit about what supercomputers do, and you heard that already from Domenico, and then I will say what supercomputers still can't do, and Thomas sort of led the way into the future, and I want to go a little bit further in the future. So we have learned in the last decade how to use supercomputers really as an extremely productive tool for science. Generally, it has been acknowledged that computing is now, as many say, the first leg of science. Computational science has been integrated in the scientific enterprise. And we use computers for doing things that were either too dangerous or that couldn't be done. As Professor Giardini showed, you can't open up the Earth, so you have to use computers to do it. I want to show you another example here, what we do with computers. And this is a simulation that is very similar to what also Thomas Schultes had shown you already. This is a global climate simulation that was done at our supercomputers, and it's about the state of the art for global climate simulations in about 2011. So what you see on top is a 200-kilometer global resolution, and what you see on the bottom is a 10-kilometer resolution. And the marked difference is that on the top, this is water vapor vertically integrated, so you see where there's rain or precipitation over the world, and you see in the top just general vapor moving around. In the bottom, of course, you see that you can actually detect on this diagram here these hurricanes or typhoons as they form over the Pacific and over the Atlantic. So clearly, the increase in resolution, as Thomas already pointed out, a factor of 10 or so increase in resolution is almost a factor of 1,000 in computing. This is the resolution from about 10 years ago. This is the teraflops era. That's the petascale area. You see we've made a huge progress there. Now, why is that important? Now you can take those data sets and you can analyze them and you can say, do we actually globally, statistically recreate the right level of storms? And so this has been done here. So this is taking this global 20-year climate simulation and extracting how many tropical storms up to hurricanes of category 5 can be found there, and you can do statistics. So this is 20-year total, what's found in the simulation. This is just category 1 and 5. That's category 2 and 5. So category 2 and 5, the Hurricane Isaac that currently hit the southern U.S. was a category 1 or category 2. Then you go further, 3, 4, and 5. And the important thing is that we can analyze the data now and can extract from the data climate extremes. And then we can, of course, compare these extremes to the actual observations. And what I've just shown you over the year shows that this computer simulation says 84 plus minus 9, doing the statistical analysis, observations 87 plus minus 8. So in 2011, 2012, we have a tool that actually accurately predicts extreme climate events such as hurricanes. So now we can use this tool and say we can do questions. And as I said, supercomputers can do things that are too dangerous to do, or experiments that we can't repeat. We currently started an experiment that we can't repeat because we pumped carbon dioxide in the atmosphere, and we raised the amount of carbon dioxide in the atmosphere, and we cannot go back to the initial conditions. But we can go in and now say what future scenarios are possible and what will these do to extreme weather events. And so we have a tool here where we can actually say if the surface temperature of the ocean rises to that level, then we might have more hurricanes. We might have more hurricanes of a higher intensity or more hurricanes of a smaller intensity. All these questions that currently cannot be answered can be answered with computer simulations. So in short, the extreme weather is a perfect example of what we're doing in computational science and engineering. In CSE, we integrate computer simulation analysis and data analysis into one big example. So we can do things that have been experiments that are too dangerous. I mean, we are doing one experiment with the climate. It's a dangerous experiment. We can do more experiments on the computer. We can ask new scientific questions that we couldn't ask before. And of course, we also learned that we're currently at a stage where we can do a few of those simulations. To do statistically meaningful simulations, we need more computer power. So relating this back to CSCS and the Swiss scene in high-performance computing, HP2C that you heard about it is a perfect example of implementing computational science and engineering. And again, I got to congratulate the Swiss community, the federal support, the centers, the universities that all work together to build these type of collaborations. We heard about it, and you heard one specific one before in geophysics. There are many others. Thomas was also mentioning some of climate. The important thing is that in all these collaborations, it's not just the supercomputer that is here, but it's the collaboration of the scientists across the country, across the world who work together on these applications. So the mathematicians would say, this building here is necessary. It is necessary, but it's not sufficient. What makes it a real success is that you build the community that you have started building. So let me move to the future. You may have seen this chart. I'm also part of this unfortunate group called the Top 500 that started 20 years ago, this exercise of listing the top 500 supercomputers. It has many good sides. It has some bad effects, but let me focus on the good sides. What you see on these curves that the computer scientists look at with great intensity is 3 lines. The red line is the most powerful supercomputer measured on this benchmark that expresses how powerful the computers could be. The sum is the total of the 500 systems, and the N500 is the lowest one. So you don't need to look at the details of those numbers, but the important thing is that you see over 20 years a straight line on what the scientists among us call a semi-log scale. What that means is that we have seen 20 years of exponential growth. So for the non-scientist, I remind you of this little riddle that you must sometimes ask your kids. You have a flower, a water lily that's in the middle of a pond. Each day it grows in size by a factor of 2. The leaf gets bigger and bigger. If it takes 9 days to get, sorry, I always get this wrong. The main point is, in an exponential growth, when you double it, after 9 days, you only half full in the pond. After 10 days, the pond is overgrown. This is what's always forgotten. I forgot how to ask the question now. But think about it. Exponential growth is something very, very unusual. We don't see this really in life. And here we have exponential growth driven by Moore's law and by parallelism over the last 20 years, as shown by this top 500 list. Now, if you go further back in the history of computing, this is from a book by Ray Kurzweil, The Age of Spiritual Machines, and you know where this is going when I talk about spiritual machines. He pointed out that this is not just on digital computers, but this goes back to the beginnings of computing technologies, up to tabulators in the late 19th century, the first mechanical computing devices. And not only have we seen an increase in computing power on an exponential scale, but we've actually seen an acceleration of this curve. So the Kurzweil argument then goes further and says, well, let's see how much $1,000 of computing buys. And you again see this exponential curve. So you see these powers of 10. And then you see these magical lines. And according to this magical line, in the year 2000, you could have bought enough compute power that would be equal to the intelligence of an insect. And here we are, the mouse, and the humans will be reached somewhere between 2020 and 2030. And all humanity can be simulated by $1,000 worth of computing by 2060. So this book is about 10 years old. And just like Thomas, I was working on supercomputers at that time and had access to one of the first teraflop computers, which is here. And I figured out this computer is not as smart as a mosquito because I can show a mosquito a rock and a piece of steak, and the mosquito knows which one to eat. My supercomputer does not know how to do this. So something is wrong. And I started thinking about this argument a little bit. And of course, there's a very simplistic model in there. And this was the motivation for the title of my talk. And this is from a book by Hubert Dreyfus, Critique of Artificial Intelligence. It's a book that was originally published in the late 60s and then republished after 30 years, what computers still can't do. And the main point here is actually expressed in this one quote. The computer model turns out to be not very helpful in explaining what people actually do when they think and perceive. This is a great fallacy. The computer might be a good analogy, but it doesn't tell us anything how we really think. And the best example is, for me, the story of Deep Blue. That's now also more than a decade old. That was the first chess computer that actually beat a human grandmaster and did this with Garry Kasparov. And the interesting thing is, even if we could analyze that computer program, it would not tell us anything how a human chess grandmaster thinks and wins a game, because it works completely different. This works with deep, brute computational force, exploring many, many, many positions that a human cannot explore. So humans do something completely different when they play chess. So the simplistic model of more and more flops gives you more and more computer powers is, I believe, is a wrong model. One indication that I'd like to mention here is this intelligence model by Gardner, who said there are 6 dimensions of intelligence. He later on revised it to 8 dimensions. Clearly, intelligence is multidimensional. I bet that 100% of the people in this room are sort of top intelligence in either logical, mathematical, or verbal linguistic. These are the categories we measure. We measure in our tests. We measure in terms of deciding admission to universities, many of these things. I bet also some of you have a very big difficulty of finding the train station from here when they had to walk. This is because many of us who are sitting in this group here don't know anything about spatial intelligence. And I'm pretty sure, and I can talk about myself, is that I'm terrible in dancing, and I think this seems to be an anti-correlation. So there are many other dimensions that would be considered intelligence, just depending on what is important to succeed in your society. So for example, Pacific Islanders have much higher spatial intelligence because they have to find their way around on the open ocean in the next island. So with that in mind, I give you a very simple current state of supercomputers and intelligence. If you assume just for a moment that the human capability in all these different dimensions is the same, what we have done so far is we've built supercomputers that look like this. As Thomas pointed out, what they do is they add and multiply floating point numbers, and they do this very fast. So, of course, we have built these really, really specialized systems that are extremely powerful in this one dimension, way, way far above the human intelligence. But we have not done very much in the rest. And what's more important is that we have built an architecture, we've found a way of making this happen, but it's not clear at all that this is the right architecture for, in a sense, reproducing all these other human endeavors. So with that in mind, I'm coming back to the Swiss scientific environment and the Blue Brain project that's here at EPFL and that may have in the future some possible connections to CSCS is an important step in this direction. The long-term goal is to build a detailed functional simulation of the physiological processes in the brain. And of course, they're at the very beginning at this point. They've done one column that's about 10,000 neurons. The whole brain has of the order of billions of neurons, so we're still very far away. But it is very important that this project is being done, because in this project, one goes about and looks at what do we really have to do to address the human performance. So just to continue on this slide, I've pointed out that we need to take different approaches in trying to understand what human intelligence and what the human brain is doing. And it's a remarkable project that happens here in Switzerland with the Blue Brain Project that is trying to attempt to help our understanding and is using supercomputers. Now that connects back, and I know that scientifically that may be actually is a competing project in some sense. This is the group from Dharmendra Modi at IBM Almaden, and I'm using this A because I've been working with this group, but also because I have detailed data. In this group, there's a different approach of doing brain simulations, and for this group, there are data available in terms of how different brain sizes have been scaling up with different computing technologies. And so we have been able to simulate of the order of a rat brain and then a cat brain on previous Blue Gene P type systems. And I just want to use the data from this chart and overlay it towards exascale. And as we overlay this towards exascale, if you take the 2009 simulations, we have a paper coming out in SE12, so I don't want to preview this paper here. But if we take the 2009 simulations and extrapolate them to where the full human brain would have to be, that is, the 2009 simulations were about 4.5% of human scale and 1/80th of the human processing time, and required about half a petaflop and 144 terabytes of memory. So we did an extrapolation very simply and say, suppose we want to do 100% of human scale, so that's about a factor of 25. We want to do real time, that's about a factor of about 80. How much memory, how much do we need? We come up with a number of 4 petabytes and a bit more than an exaflop. So going back to Thomas's presentation, the exaflop was this magic number that all of us are thinking about in about 2018 to 2020. So by about 2018 or 2020, we may have a resource available that actually would allow us, if all these extrapolations pan out, to actually do a full-scale brain simulation to some extent in real time. So that's terrific. Of course, where this all will come together, the Markram group predicts it will take until 2023. Doesn't really matter. It will happen the next decade or so. But, and this is the one last thing that I want to point out, there is still a huge conundrum. As I said, the straightforward extrapolation will get us there in about the next decade. 1 to 10 exaflops, 4 petabytes of memory. However, and you also heard this already in Thomas's talk, an exaflop computer will take 20 to 30 megawatts. 20 to 30 megawatts. The human brain operates at 20 watts. Your whole body takes 100 watts. That's sort of a strong light bulb. That's actually pretty remarkable. I mean, we've evolved into a very, very efficient, energy-efficient system. So the human brain to a supercomputer is a million times more efficient. And so you've got to pause about this, because a factor of 1,000,000 cannot be overcome with some little engineering methods. We really have to fundamentally rethink how we do computing if we ever want to build systems that have true cognitive computing capabilities, because there are questions of technology and architecture that just haven't been addressed yet. In the current generation of CMOS-based traditional supercomputers, we are not going to get there. We have to think differently. So with that, I want to loop back and I say, you have the tools here. You have the scientists to ask these questions. You have visionary leadership who has invested in computational science and engineering. You have a wonderful community that works together at the local, at the cantonal, and at the federal level. So the field is open for you to make big progress in solving some of the most fundamental problems in science. Congratulations.